Puzzles 2017.
All right, welcome everyone. Sorry for the surprise and TBA-ness. I wasn't sure what I'd talk about, but I figured it out last night. So today's talk is going to be about USB Type-C and what that means for DMA attacks against Windows specifically, and also some EFI realizations that come across with that, especially in the light of Type-C becoming much more prevalent in all sorts of new machines out there. So just a little bit about myself. I live and dream in Windows. When I go to sleep, I just see kernel code. And I've been doing this for about 17 years now, which seems like a really long time. So I like to look at Windows and operating systems in general, and mostly dabble on the software side, but every once in a while, I like to remind myself that there's hardware too. So I've done some stuff around SMC, firmware, and today I'll be talking about Type-C and Thunderbolt. So basically, what's happening these days is there's starting to be cheap, non-FPGA-based, affordable USB to PCIe devices. For example, like the one I've got right here, which is a few $100s, which is still expensive, but it's way cheaper than other kinds of devices that would give you access to the PCI bus, which are actually either thousands of dollars, or you need to buy and build your own FPGA and do your own programming of it. Second thing that's happening is Type-C is bringing Thunderbolt 3 to Windows devices and not just Mac devices. So this is leading to an explosion of Thunderbolt 3 capable devices, and Thunderbolt 3 is basically PCI Express over cables. So we're starting to get USB to PCI Express becoming a commodity. We're starting to see PCI Express over USB Type-C become a commodity. And so combining this together, we can now very cheaply have access to the PCI Express bus of another machine over the USB bus from another, which is exactly what I'll be showing today. So this used to cost, for example, $9,199. You can still buy this today, something called a capture guard. And if you've got $9,199, you buy one of these cards, and then you can do memory acquisition and lost password recovery on other machines. But with modern hardware today, you can rebuild pretty much exactly that for about $350. And that's if you're lazy like I am, because otherwise you could just actually buy the chips that you need, and it would cost you probably about $50 instead. But if you just want to buy, ready-to-made cards, plug them in together, that's $350. And again, it's not cheap yet, but it's still a lot better than $9,199. So I'll talk a little bit about previous research around the space, because obviously there's been a lot of work done around external DMA attacks, around Thunderbolt, so I just want to point out the existing body of work around that. I'll talk a little bit about Type-C, and specifically Thunderbolt 3 over Type-C, kind of how that looks like and what the security is. And then I'll talk about a very specific, very special chip called the USB 3380, which is going to power this whole attack. I'll briefly talk about something called the User Mode Driver Framework, or UMDF, which is a really nice Windows built-in framework for writing PCI and USB drivers in about 2 hours of code. So if you can do C, you can probably write PCI Express drivers in Windows now. And then I'll talk specifically about some very interesting Windows physical memory forensic details, some structures that are in physical memory that are often misunderstood. We'll get to the bottom of where those structures live, why they're there, and the interesting data we can get from them. And finally, we'll talk about how to actually mount an attack using everything we've learned, specifically targeted towards Windows, leveraging some of the stuff that EFI is going to make possible for us. And then we'll wrap up with some concluding thoughts on this. So, of course, I want to point out, as probably many of you know, that external port DMA attacks have been around for a while. I think one of the main popularized ones was with FireWire against Apple computers, where you could plug in a fake iPod or something, a Linux machine that pretended it was a laptop, an iPod. And because FireWire essentially gave you DMA access and bus mastering, it was a really nice way to externally attack Mac laptops and a few of the Windows laptops that had FireWire as well. This was also doable through ExpressCard, because when ExpressCard came out, it was essentially a PCI Express bus inside of your laptop. So there's been other attacks against other types of ports that at some point were very prevalent. Of course, today no one has ExpressCard on their laptop anymore. No one probably has FireWire on their laptop anymore. Those initial attacks actually led to some changes done by OS vendors. One thing that happened is many OSs stopped allowing bus mastering and or DMA until the user logged in. Or they applied blocks on generic classes of devices. Or simply when the machine is locked, they don't allow certain operations to happen. At the end of the day, though, for compatibility reasons, there are certain device classes, though, that still end up having bus mastering. And of course, if you can own and control the device ID and the vendor ID, you can still pretend you're one of those devices that still gets bus mastering and still gets DMA. But it was kind of the first time that OS vendors started locking things down. Now, over Thunderbolt specifically, which became very popular thanks to Apple, Snare, of course, did some attacks against this, such as the Demysterious Jobsys, and then, of course, Trammell Hudson with the famous Thunderstrike attack. A lot of these, first of all, relied on option ROM. So the idea was that you plug in PCI Express hardware over Thunderbolt, and then the option ROM would execute and execute malicious payload against the machine. And that works specifically really well against Apple computers because Apple UEFI is essentially based off UEFI 1.12 with lots and lots of improvements, but it doesn't have Secure Boot enabled. So without Secure Boot, option ROMs just execute, and there's no authenticate code signing or anything like that. Now, very recently, Apple has actually closed off a lot of those attacks. Now, option ROMs don't execute at all anymore unless you press a special sequence. So again, thanks to Trammell and Snare, Apple locked down a lot of their interfaces as well. On top of that, we now have IOMMU or VTD that's enabled by default on Macs as well, which prevents against DMA access, even if you can do it, around OS-based memory. So you have to first bypass the security around that. Now, again, these attacks were really useful, but because they relied on Thunderbolt or Thunderbolt 2, they're limited mostly to Mac hardware. There's very little Windows machines out there that had these types of ports that you could influence. What changed is a presentation done a few years ago by Joe Fitzpatrick. And Joe Fitzpatrick discovered this USB 3380 device, which essentially gives you a USB 3 to mini PCI Express interface. Got one right here, very tiny little device, PCI Express, mini PCI Express on one end, USB 3 on the other. And you have a very small package that gives you essentially a bridge between any commands you want to send across USB and that you want to see across PCI Express, or vice versa. Right? And this really is a game changer for the types of attacks we're going to talk about, because this used to be giant boxes and FPGAs or very expensive hardware. This is basically $150, and you can probably get it for cheaper than that if you wanted to make your own equivalent one. Now, it has one problem, which is it can only do 32-bit DMA. So one of the big problems around the attacks were, how do I attack a modern operating system, which of course has physical addresses above just the 4 gigabyte range? The initial usage of this device also was only about 3 megabytes a second. Joe was using the PCI in and PCI out endpoints, which essentially just do configuration register access, and 3 megabytes a second can take a while to mount an attack. And also, unfortunately, this type of hardware doesn't allow you to have an option ROM. It lets you modify lots and lots of registers, but you cannot provide an option ROM with it. So you can do DMA attacks, but not directly have the OS execute code. Ulf Frisk then, a few years later, modernized the attack by adding DMA support to this little piece of hardware, because it actually has, as we're going to see, 4 DMA endpoints. And by enabling the DMA endpoints over USB, you can now do attacks or dumps at 150 megabytes a second over USB 3, which is a hell of a lot faster than 3 megabytes. He also basically bypassed the need to have the official toolchain from the company that makes a chipset, which is under NDA, which only worked in certain operating systems. So he originally wrote a Linux driver that allowed flashing the hardware, and then after that it could be used from Windows as well. We also figured out a really simple way to talk to the USB side, which is to simply program it and pretend it's an Android phone or a Google Glass, to be more specific. And then with a simple Android driver on the Windows side or any side, you can talk to the USB port. So this made it a lot more usable, and he has a GitHub with implants based on this device for Linux, for Mac, and for Windows, typically leveraging Thunderbolt 2 or going through various kinds of interconnects in the middle. So there's already a huge body of work here. So, what did I do? What am I here to talk about? Well, first of all, I fixed some small bugs in the actual firmware that most people have been flashing on this. I looked at the data sheets and realized some of the registers were off. This chip has a little bit of stability issues. If you touch some wrong parts of RAM or if you dump memory too quickly, there's lots of things that are going to make it basically die out. So I figured out how to basically make it work a little bit more reliably, especially if you actually use USB 2, which is a little bit slower. You'll get about 50 megabytes a second. It's a lot more reliable. And instead of relying on a Linux PCI driver to actually flash the EPROM, I created a UMDF driver, which I'll talk about, which basically means it can easily be used in Windows now without requiring to boot in a Linux partition at first. And most importantly, part of this talk, figured out a universal implant technique that works always with memory under 4 gigabytes, so that you don't have to basically hunt for specific OS techniques to get access to something that'll let you execute the implant. Using EFI runtime services, we can actually do something pretty universal, and we'll see that UEFI is always under 4 gigs. Specifically on Windows, we're also leveraging the HAL Heap, so I'll talk about the HAL Heap and kind of how it's relevant to this, and also modernize the attack to work across USB Type-C. Because again, the original attacks were done over Thunderbolt, so a few limited Windows laptops and mostly Macs. With Type-C, this opens it up to basically everything. So again, important to acknowledge all the work that went in before that. So first of all, let's talk about kind of Type-C and Thunderbolt 3. So basically, Type-C is a specification for a connector and a cable. It's basically a reversible USB connector. It can support up to 100 watts of power delivery at 20 volts, which is huge. And the key thing about this cable is it can be programmed to support alternate modes. And there's so far 3 standards for alternate modes. There's a DisplayPort alternate mode, a Thunderbolt alternate mode, and an HDMI alternate mode. But in theory, you could drive Ethernet over this cable as well. You could drive basically anything that can be signaled accordingly over this cable. And so with Thunderbolt 3, since about June 2015, you can now route Thunderbolt 3 signals over Type-C. A little bit slower than default. Thunderbolt 3 can go at 40 gigabits. Over Type-C today, it's still only 10, but there is Generation 2 coming out, which will add it. Then Skylake chipsets, which are the almost latest Intel chipsets, so before Kaby Lake came out this year, Skylake chipsets now have native Thunderbolt 3 controllers in the actual chip. So most brand new Windows laptops, and even Windows laptops from about a year ago, like this is a used Dell from a year and a half ago, now come in the mid-range option usually with the Thunderbolt 3 or USB Type-C connector. Apple MacBook Pros, of course, now come with 4 of them, and new motherboards as well that are coming out now have Thunderbolt for desktops as well. So we're really seeing an emergence to USB-C from Apple and also from PC manufacturers. Now, Thunderbolt 3 specifically is a highly proprietary standard. Even to use it on Windows, you need special Intel drivers that your PC manufacturer is supposed to ship. Windows does not have a built-in Thunderbolt 3 driver, and from what I've heard from my friends at Microsoft, they don't even have access to the specs, so they can't even write a driver. It's highly NDA'd by Intel. Then your BIOS actually also needs to support and enable a Thunderbolt 3 controller, specifically to enable some security levels. And the way it works on PCs is if you plug in a Thunderbolt 3 device, the driver is actually going to notify you new Thunderbolt device has been attached. And you actually have to be an administrator, press OK, then you get a dialog that asks you, would you like to enable this Thunderbolt 3 device? And you can say, just this time, nope, or always allow. So you have to, as an administrator, manually authorize the connection of a Thunderbolt 3 device, which in theory sounds pretty secure. Of course, the question is, is that admin dialog a security boundary? Does the driver have an undocumented ioctl? I haven't looked at it, I don't know, but history would suggest there's probably a way for non-admin to click that button anyway, but that's not what I'm looking at today. I'm not dissecting the security of that driver. But by default, you get a little pop-up there. Now, that actually depends, though, on how you've programmed your BIOS. So this Dell laptop has a few options. For example, it has an option to set the security level, and by default, security level is set to user authorization. This is what makes Windows have that little pop-up through the Thunderbolt driver. If I set it to no security, then that pop-up won't matter. As soon as I plug in the device, the controller will activate it. Secure Connect means that the device not only gives you a pop-up, but actually has a unique ID. And in theory, if you plug in any other Thunderbolt 3 device of the same type, but with a different serial number, it'll still basically recognize that. So I might either authorize this thing here, or I might authorize any kind of Thunderbolt 3 boxes by the same manufacturer. So the default level, if I authorize this one, it authorizes all other ones like it. The idea of Secure Connect is it only authorizes this one. And the most secure level is DisplayPort only, which basically turns off PCI Express signaling. It only allows DisplayPort as an alternate mode. And of course, there's supposed to be no data over DisplayPort alone. Of course, what's interesting is the Dell laptop has, by default, always allow Dell docs. And I haven't looked at this. I would have to reverse engineer the firmware, but I'm willing to bet that always allow Dell docs mean if you have the vendor ID of Dell and the device ID of doc, you'll probably get through and bypass this. And this is set by default. You also have some other options which are not on by default, but they're very interesting. One is to enable Thunderbolt at boot, and one is to enable Thunderbolt and PCI Express behind Thunderbolt pre-boot. So this basically gives you access to the second you power on the machine, you'll have Thunderbolt 3 access, and this one is while the machine is booting up, you'll have Thunderbolt 3 access. So highly configurable, and by default, always allow Dell docs is on, and user authorization is on. I've also manually enabled the boot options, just to have a little bit more fun with the device. So here's some interesting facts about this, though. If you enable Thunderbolt 3 pre-boot or at boot, you basically give up the security, because EFI does not have a little pop-up to ask you, do you want to allow the device or not? So regardless of the security level that you set, as soon as you enable Thunderbolt at boot, you're screwed. Because as soon as I plug it in EFI mode, I'll have full access to EFI firmware, regardless of secure boot settings. So already I could inject something in the machine at boot. But even after boot, Windows does not reset the bus, or rather the Intel secure driver doesn't reset it. So as long as they don't unplug and replug the Thunderbolt 3 device, if it was plugged in at boot, it'll silently remain active regardless of the driver and what it says. So it basically bypasses completely the whole point. Obviously, if you turn it on in legacy mode or no security, this also completely bypasses the authorization. And while people are still going to have Thunderbolt devices and Thunderbolt 2 devices, in many cases, they're likely going to need to enable legacy mode. In fact, just searching on Google last night, going over a few forums, I saw a lot of forum posts from people saying, I can't get this to work, what should I do? And people suggesting, oh, just set it to legacy mode or no security mode. The other thing that's very interesting about this, and I can't show it to you because I can't dual project, so just trust me on this, is when I plug in this PCI Express to Thunderbolt 3 device, which is designed to let you use an external video card. When I plug it in, what Thunderbolt's security driver says is you're plugging in a PCI Express box, and I authorize it. Once I've authorized the box, regardless of what I put in the PCI Express slot, it's authorized. So if I normally have a video card in here or some other PCI Express device, and you come in, and which I've authorized, and you come in and swap it out and put a different card inside, I'm owned. Because even in the strongest secure ID, unique ID mode, it still doesn't recognize that I've actually got a different PCI Express device plugged in the bridge, which seems completely broken to me. So you're authorizing the bridge, not actually the device that's going to be on the bridge. And then, of course, with the default, allow Dell docs by default, I'm pretty sure if you just put the right vid and did in there, maybe there's a symmetric key, who knows. Pretty sure you can bypass that as well. So there's a lot of nice security toggles, but in practice, they're not really strongly implemented today. So let's talk about the 3380 itself. The 3380 basically is a $15 chip. Now, with the dev board, it's a little bit more expensive, and it gives you PCI Express Generation 2 to USB 3.0. Has 4 DMA channels, so you can do in and out, depending on how you program them, and has 2 PCI channels as well, so you can set MMIO, touch PCI configuration registers, and so on and so forth, and it has specifically channels for configuring the device as well. So you can access almost any PCI header register, almost any USB register, and the idea is you can kind of implement your own USB device or implement your own PCI Express device. On top of that, it even has on the chip, on the controller, an 8051 microcontroller, and that 8051 microcontroller can be connected to an EEPROM, and it can actually have code that executes. And that 8051 has full access to all the registers as well. And there's a company in Taiwan or China, I'm not sure, they have both websites called B+, and B+ will actually sell you some development kits. They'll sell you the PP3380, which is an actual PCI Express card. That one has an 8 kilobyte EEPROM. They'll sell you the USB 3380 EVB, which is what I showed you earlier, which is the small mini PCI Express version, which has only a 256 byte EEPROM. And they also have an Express card version, but no one has been able to actually get that to work with some of the attacks we're going to talk about. Now, unfortunately, a few months ago, PLX, who actually makes the chip, got bought by Broadcom, and now you need an NDA to access the data sheets. You need an NDA to do anything. So thankfully, I got all the stuff before the acquisition happened. Otherwise, I have to sign up with the Broadcom account and worry about that. Again, though, it has a few problems with the chip. Can only do 32-bit DMA, so you're stuck with addresses below 4 gigabytes. And also, if you do DMA to an incorrect address, basically a memory hole or reserved region of RAM or an MMIO, the device will usually lock up. In some cases, you actually have to power it off, wait a few seconds, power it back on. It's not enough to just replug and unplug. The device dies if you DMA on valid memory. And of course, both of those are big issues because modern operating systems have memory above 4 gigabytes a lot of times, most of the time. And you don't know ahead of time what the physical address space of the other machine looks like. Obviously, there's some well-known addresses like SMM RAM that you should never touch, but you might touch some specific memory hole on this Dell, and then the whole device locks up, which makes attacking and reliability a lot harder. And this is kind of what interested me. Can I find ways to make this a little bit better? So out of the box, when you buy this 3380 device, it's in a kind of an inert state. The PCI Express interface is active, but the USB side is not. So you have to flash it with your own custom serial EEPROM, and that serial EEPROM has basically up to 256 bytes at minimum of configuration registers, and you can, through the EEPROM, configure how this device is going to act. So you can configure the PCI ID, the device ID, and any other control registers that you want. So at minimum, you need a little header. Then you can specify the size of the firmware, and then in this case, we are setting the USB control register to this value, which if you look at the data sheet, basically enables the USB side. So if we set these bytes in the serial EEPROM, this will then enable the USB controller. That's kind of the very basic step. And the way the firmware works is it's all big endian, and you take the register that you want to modify and you divide it by 4 into a register index. So if you want to modify register 8C, divide that by 4, that's 0x23. And then you specify if it's a USB controller register or if it's a PCI Express register. In this case, it's USB, and then the data comes after that. So this is how we're setting this value in the USB control register. Now, other things we'd like to do is give this thing a more interesting PCI Express vendor and device ID. For example, Broadcom SD reader. This is actually going to give the device bus master access even during logon, even before logon. So we're going to configure PCI register 0 to give us that PCI vendor ID and that device ID. Then we're going to program the DMA endpoints. One endpoint for out, for writes, because we're likely going to want more speed on reads, less on writes, and 3 different DMA endpoints for reads. Each of these endpoints can do 16 megabytes a second, so you can do the math. That gives us a pretty fast transfer speed, especially we can multi-thread things as well. So now we've got our DMA endpoints active. We've got a fake PCI ID. The last thing that we need to do is, for example, set up that Google Glass USB ID. This will make the USB side look like a Google Glass. It'll make the PCI Express side look like a Broadcom SD card driver. And this is essentially a standard serial EEPROM that, for example, Ulf used in his attacks. Again, the Google Glass is just so we can then drop an Android ADB driver without having to write a custom signed driver for that. But we'll see you don't necessarily need to go down that route. Now, one thing to mention is that a PP380, that PCI one, not the one I'm using, actually has an 8 kilobyte EEPROM. So because the 8051 chip that's there, which is normally not running, has full access to USB and PCI, this entire attack that I'm actually doing through 2 separate machines, I could have implemented all of this in the 8051 EEPROM in a single tiny device that just plugs in a USB-C port, right? So it doesn't have to look this unwieldy. It can be a simple Type-C device that, with the right ASIC, or even this little chip, you plug it in with a little EEPROM on it, and you mount the attack directly. In this case, we're going to mount the attack and the reads from this machine to the other, but because it has its own chip, it's very easy to just program the code directly. And again, this is very surprising, right? Because before this type of chip, you had to have your own FPGA, do its narrative, for example, which is put MIPS on it. This just makes it much, much, much easier. You, on top of that, even have some nice little diagnostic LEDs that B+ put on this. You have 4 LEDs, 3 orange and 1 blue. And this can be very useful during development, actually, blink the LEDs and see what's going on. And specifically, if you're using 8051, you can use the LEDs as kind of signaling to know, okay, I'm connected, okay, the DMA worked, okay, the attack is at this stage. It's a really nice, neat little package that basically has everything you could need. It's almost like they thought about what their target market was going to be. So you plug it in without the firmware, and you're going to see a USB serial port controller on one side, and you're going to see nothing on the other. So the first thing we need to do is program that serial EEPROM. To program the serial EEPROM, we need an actual driver to attach to the PCI Express device, memory map the bars, and then access the registers to program the serial port. So for this, you need a driver. Now, writing PCI Express drivers sounds like a really hard thing to do, but it turns out that Microsoft made it really, really easy with something they call UMDF, which is the User Mode Driver Framework. And I'm not going to teach you how to write a driver, but I'll basically show you in a few slides just how easy this is. So we need a driver to map the MMIO range on the PCI Express device, and we need to flash the EEPROM. Now, a real kernel mode driver is hard to write, leads to blue screens of death, and also has to be signed. Especially in the latest versions of Windows 10, it has to be signed by Microsoft, submitted to the WCAG certification page, and tough luck getting a DMA attack driver serial EEPROM flasher signed by Microsoft. Now, the nice thing is that UMDF, in specifically Windows 8 and later, now has full access to the PCI Express bus, and with the right settings in your INF file, you can actually just memory map PCI Express memory in user mode and natively access it, as well as natively access any registers as well. And UMDF drivers are DLLs that run in user mode, and so you don't have all the strict signing checks. In fact, the only signing check is at installation if it's signed by something in your local trust authority. So, for example, what Ulf did when he published the Windows driver is he just basically wrote a little installer that has his certificate, installs it into your trusted roots, installs the driver, and then deletes the certificate. Once it's installed, there's no load time checks whatsoever. So technically, user mode drivers don't have to be signed when they load. They just have to be signed when they were installed, and they just have to be signed by something in your local certificate store. Unlike real kernel mode drivers, which are much more hard-coded than that. So basically, a UMDF driver just needs an INF file where you configure these two settings, allow direct hardware access and register access using user mode mapping, and then you put in the PCI device ID that you want to control. And the first one here is when the device comes up in its default state, basically before we program it, and this is after we program it as a Broadcom SD card reader. So this can act as a driver both for the original unflashed device, also after our custom flash. Once you have the INF file done, basically like 3 lines of code to create your driver object, 10 lines of code to then create the device, which will react whenever the device is plugged in. And then when the device is plugged in, that's when you have 15 lines of code to basically enumerate the resources, find the RAM bar, see that it's 8 kilobytes, which is the default size of the the MMIO range, basically map it, and now it's mapped in user mode, and we can flash it. And we're pretty much done, except if we want to be good programmers, we also then need to clean up when the hardware is released. So 4 slides of about 40 lines of code, and we've got a PCI Express driver, and it doesn't need to be signed, and we can flash the firmware on this thing. Once we've done this, then basically it'll come up as an Android Google Glass device, and just getting the Google drivers, which are already signed anyway, they're user mode drivers as well, will now give us a WinUSB interface. Now, long term, my plan is to actually write a proper non-Google Glass relying USB driver for this using UMDF. But because Ulf has already done all the work with his PCI Leech tool, I didn't want to reinvent the wheel. So to keep his tool working with some of the stuff I'm going to show, I just kept it as a Google Glass, so then it works natively with his code. PCI Leech is really, really nice. It can do a whole bunch of things. Here I've basically extended it for some of the things we're going to be talking about in this section. So now I've got a Google Glass on one side, and I've got a PCI Express device on the other. So now what are the fun things we can do with this? Because now I have DMA access to the bottom 32 bits of memory. Well, first I want to talk about the HAL Heap. The HAL Heap is something I first talked about at Syscan about 5 years ago, using it as part of some ACPI physical attacks. And ever since then, people have found more and more interesting ways of abusing the HAL Heap. But there's a lot of misunderstanding exactly about how the HAL Heap works, where it is. A lot of people say that it's static, when in fact it isn't. So I really want to drill down and kind of have the final word on what the HAL Heap is and what it means for you. So the HAL Heap is basically how we refer to a special region of our address space that the kernel, the bootloader, and the Windows hardware abstraction layer, the HAL, pre-allocate or pre-reserve even before boot. And the virtual address space of this has always been FFC0000 until FFFFFFFF for a total of 4 megabytes. So everyone kind of knows not to touch this region. That's where the HAL can allocate things. Because the HAL needs to allocate things before the memory manager comes up. So we need to make sure the memory manager never tries to use those virtual addresses. Then a megabyte after the beginning of the HAL space is where the heap itself starts. So the HAL heap and the allocations the HAL makes are 1 megabyte after the beginning of the address range, which is FFD 000000. And on 64-bit, this is simply sign extended, so it becomes FFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFFF and then we can get some data there, except in Creator's Update. So in Windows 10, coming out this April, Redstone 2, they have now randomized this region. So it no longer is at that address, and it is the final kernel mode address that had resisted randomization for many, many years. Now this is going to be randomized as well. The bootloader basically decides where to put it and tells everything else after that. But we're going to see with physical access, there's some ways around that. Now, in a lot of places, the HAL heap in physical memory is set to begin at 0x100,000, especially on older versions of Windows. For example, even on a blog on core security called Extremely Abusive Intel Page Tables, which is a really good presentation, but there was this assumption, oh, the HAL heap at 0x is at 0x100,000, and it's at 0x1000 on Windows 8.1. And that's because, yes, usually there is some memory there. But actually, in some cases, the researchers weren't really looking at the HAL heap. They thought there were. So we'll talk about what exactly is there. And they don't have to, the HAL heap doesn't have to be at that address. We'll actually see where it's really going to be. Because the physical allocation isn't static, but it can be predicted if you understand where it comes from. Same thing for the virtual addresses. Even before Redstone 2, people kind of assume that within that HAL heap range, certain allocations are always somewhere. But that's actually not the reality. And finally, within the region that we call the HAL heap, there's actually an actual heap in there, and then there's actual other allocations that are made as well. So the HAL heap is kind of a very misused word, because there's the HAL address space, then there's what Microsoft calls the HAL heap inside the address space, and then there's a heap inside that HAL heap address space, but there's other non-heap stuff as well. So obviously you can understand why people get confused about all of this. So first of all, let's see how allocations come to be in this heap. So first of all, we have the HAL virtual allocator. And the virtual allocator is very simple. It starts at a base address, which up until very recently was FFFD0000, and it just grabs the next available virtual address. So there's no randomization or ordering here, just the next available virtual address. The physical allocator, which then decides which physical page is going to be mapped behind that virtual page, is a little bit more complicated. First of all, it checks for a special flag called discard low memory, which you can actually enable with BCDedit, as I'll show you at the end. On APIC systems, so on systems that have an APIC, which is most systems today, this is set by default. So discard low memory is automatically turned on. If you have a PIC system, like a really old, x86 with a single CPU, then it is not disabled. So it's disabled. So they do not discard low memory. They use low memory. Also, if you have Hyper-V enabled and you're not booting on the root partition, it'll also be disabled. So we're going to use low memory. Then it's going to check what is the maximum physical page you're willing to accept for this allocation. Because whenever you allocate memory through the HAL, you specify what's the maximum. If the maximum is below 1 megabyte and you have less than 1 megabyte worth of pages and discard low memory is disabled, we're going to pick 0x1000 as the first address. So it's going to start allocating at 4 kilobytes, so page 1, page 2, page 3. If, on the other hand, discard low memory is turned on and there is no requirement for your physical address to be below 1 megabyte, then we're going to start at 1 megabyte. And at 1 megabyte, we're going to find free pages or temporary firmware page. Anything that's marked as firmware temporary or as free starting at 1 megabyte. So basically, there's two possibilities. Either we allocate starting at a meg or we allocate starting at 4 kilobytes based on the type of machine you have and based on what the requester actually wants. So here's an example of a machine at boot up. We can see here that the HAL has started using page 103 because it started at 100, but I already had something at 100 from the bootloader. I already had something at 101. I already had something at 102. So it started allocating at 103. So for example, on these machines, the HAL heap doesn't start at physical page 0x100. If any tag that assumed that would break automatically because I actually do have 3 allocations here. On my other machine at home, it actually does start at 100. So it'll start somewhere near 100, and you are guaranteed that the pages will be contiguous until you get to the beginning, but you might have to do some scanning. It's not necessarily going to be 0x100. Or it could have actually been starting at 1 if I had a PIC machine or if I disabled discard low memory. So that's where you get a little bit of variance. Now, what actually lives in this HAL heap? Well, any allocations that are done very early at boot by the HAL before the kernel has actually initialized the memory manager. So there's an actual heap that is used by HAL allocated memory. There's ACPI, so whenever ACPI tables are cached, it uses the HAL heap. Also something called allocate early pages, so whenever a driver wants early pages, it uses the HAL heap. The page tables for the HAL heap itself come from the HAL heap. And if you have a kernel debugger plugged in, there's some allocation that's going to be coming from the HAL heap as well, plus any DMA buffers that need to be allocated there. So there's a whole bunch of stuff that uses the HAL heap. So the structure of how it's actually going to look like in virtual address space is also going to be a little bit different. For example, if you have kernel debugging enabled, then the very first thing that gets allocated in the HAL heap is going to be a kernel debugger structure, a little structure that HAL uses to identify the physical device you're using for kernel debugging. If you don't have a kernel debugger attached, then the first allocation that's going to get made is actually going to be a timer object, and a timer object lives in the internal heap, so the base address of the internal heap is going to end up being a little bit different. Because debug devices come from the internal heap, and if the first thing that we allocate is a kernel debugging device, the internal heap begins here. If, on the other hand, you don't have kernel debugging, then something else is actually going to use that address, and we're going to see what it is. And then the first internal heap allocation actually has to start a page later. So the actual internal heap, part of the HAL heap, doesn't by default actually start at the beginning of the HAL heap. It actually starts a page later, unless you have a debugger plugged in. So you can imagine why a lot of researchers probably, when they're doing their work, they have a debugger attached, and so they think this is actually the beginning of the internal heap, when in fact, in most cases, it's going to be that other address. And this is pretty deterministic, so it's going to be one of those two, depending on if you have a kernel debugger plugged in or not. Then within that internal heap, like I mentioned, the kernel debugger device might be registered. Then a timer object gets registered. Then a USB controller gets registered. And if you actually do have kernel debugging, then a secondary copy of that debug device gets registered. So ultimately, if you watch the allocations that are made there, which are always done in the same order and they're always the same size, you can pretty much predict what it's going to look like. And so, this is a diagram that will make more sense on the next slide and once I publish it. But basically, this is the entire space of the internal heap in the HAL. And you can understand, you are able to understand once you know the allocations what every one of these things is. So on every machine, while you're booting up, the HAL heap is going to have the same allocations, at least for Windows 10, right? Obviously, Microsoft can add more code in more places, and this can change, but it is hyper-deterministic once you know where to actually start. So, for example, this is mostly for reference. On that earlier picture, these are all the allocations we're able to see with their fixed size and their fixed data types. In fact, one of the interesting things I noticed while doing the analysis, there's actually a bug in a code in the HAL that allocates double the amount of space that it needs. It takes a Unicode string that already has the number of bytes, and it thinks it's a number of characters, and it multiplies by 2 again. So, there's a little bit of a waste in the HAL heap as well, but it can all be understood once you see what the static allocations are actually going to be. So what have we learned here? So first of all, we've learned that if the kernel debugger is attached, then FFD000 is going to be the internal size of the HAL, and then the internal base address of the HAL, and then the first timer object is going to be at 0xF8 plus some variable size. Because the first allocation is actually going to be the debugger object, then the timer object. If you don't have kernel debugging, then something else is going to be at FFD000. You can wait for it. And the HAL heap will actually start at FFD01000, and the first object there will be a timer object. Now, what's nice about that timer object is it's got some callbacks in it. And essentially, if you have an arbitrary write vulnerability, either in virtual memory or in physical memory, you can patch one of the timer object callbacks, which is going to be a deterministic address, right? It's either going to be over here or over there, plus some offset. And if you patch the timer object callback, you get instant code execution. And this has actually been leveraged in the core security blog. They attack this object, but again, they made some assumptions about where it's going to be, which don't always hold true. Now, after these initial allocations, every other allocation can be somewhere else. So there's a whole number of other things that may come into place and then into play, and then it depends how many ACPI tables you have, and so on and so forth. So for physical memory, we've said that either starts at a megabyte or it starts at 4 kilobytes. But individual allocations can themselves specify a maximum address. So for example, ACPI cached memory and DMA memory always wants to be below 16 megabytes. So it sets that as a cap. And then another allocation called the low stub always wants to be below a megabyte. Which means that in a default system where the HAL heap starts allocating at 0x100 at 1 megabyte, because the low stub is the only thing that requests being below 1 megabyte, the only page you'll have below a meg is the low stub, and the low stub will always be at 0x1000. Now, what on earth is the low stub? The low stub is one of the most undocumented structures that I've seen in my entire reverse engineering history. No one has even talked about this ever. It is a tiny little piece of 16-bit code that still lives even in 64-bit Windows, and it's used in 2 cases. When you're booting up the processors at boot, because as some of you probably know, when you boot up your fancy Kaby Lake processor, what does it boot up as? A 16-bit processor, thinking there's only 640K of memory. So we need to have some memory in 640K real mode to bring it up in protected mode and then bring it up in long mode. That's what a low stop does. Second thing the low stop does is when you bring your machine to sleep. If you bring your machine to S1, you're okay, but S2 and S3 sleep states, they wipe the CPU state. So when the CPU resumes from sleep, what does it think it is? A 16-bit processor with only 640K of memory. So the low stub reinitializes the processor, brings it back in protected mode, brings it back in long mode, and brings you back where you need to be. So the low stub has been in Windows since NT1. Never seen anyone on the internet even talk about this fact this exists. And because of the allocation policies on modern hardware, it's always going to be at 0x1000. which has some interesting opportunities. Because that low stub isn't just 16-bit code, it's a little GDT as well, a little IDT, an identity map, and perhaps most interestingly, a structure called processor state, which is documented in the symbol files and in the header files. And that processor state structure contains CR3, the instruction pointer, the stack pointer, and RCX. And so basically, you can leak at a fixed virtual address on any fixed physical address on almost any machine in the world at address 0x1000, the address of the kernel page directory, PML4 or CR3, which of course once you have this, physical memory acquisition becomes really easy. And on almost any modern machine, it's going to be a 0x1000 plus whatever the offset of the structure. You can also get the address of the kernel entry point, you can get the address of the kernel stack, and you get the address of the loader block, which is another key boot structure. Plus, what's really nice is the low stub actually has a self-map pointer, which gives you the virtual address of the low stub. So you know where it is in RAM, because it's pretty much fixed, and it also tells you where it is in virtual memory, and you know it's in the HAL heap somewhere, at some offset off the heap. So even in Creator's Update, when they randomize the HAL heap, well, you know exactly where it's going to be if you can access 0x1000 with an arbitrary read primitive or with a DMA attack. So basically, now that we have the low stub, we can get the address of the HAL heap in virtual memory. And even if you have a system where the low stub is not at 0x1000, it's going to be at 0x2000 or 3000 in the case where discard low memory is not enabled, right? Because the HAL is going to have its other allocations at 0x1000, 2000. The low stub is going to be somewhere else after that. So it's either at 1000 or somewhere near 1000 if you have an x86 PIC system, and you can just scan around that. So now we have the CR3 structure, we have the page directory, and we can now do some interesting attacks with virtual addresses. Plus on top of that, which is not a topic of this talk, that structure is used for ACPI sleep. So you have a really nice persistence point where if you put your own code in the low stub and the machine goes to S2 or S3 sleep, when it comes back, you take direct control of the CPU before anything else even gets to run on it. So that's a little bit out of scope for now, but some interesting research for later. Okay, so that's a low stub, but I also said there's another allocation that happens in the HAL at FFD 0000 if you don't have the kernel debugger enabled. If you have the kernel debugger enabled, then this is actually going to be at 0x1000. This other allocation is done super early at boot, as early as possible, except you have the debugger, and it's a structure called the ACPI bias multinode, which is a piece of code that's been around since NT1, based on an old 16-bit app real mode called ntdetect.com, which used to run on old systems to detect your hardware, and it created this ACPI bias multinode. What's that structure? Well, it's the physical address of the ACPI tables, and then an array of ACPI E820 entries. And E820 entries was the old way in the 1980s that by doing interrupt 15, you could get a physical map of all the physical pages and their current use. Which ones are holes, which ones host OS memory, which ones should not be touched, etc. Even today, on a brand new 64-bit system with EFI and with no BIOS, nothing like that, Windows and Linux still create E820 entries by either getting them from the BIOS or emulating the BIOS, the EFI map. So the EFI specification has this whole new way of creating memory maps. What every OS does is it takes that and it rebuilds the E820 map, because that's what OS guys have been doing for 20 years. That's what they want to get back to. So basically, that structure contains in virtual memory at a fixed address, essentially every single physical page and range, I should say, and if it's usable or if it's reserved. So now combining these two things, we have a fixed address in RAM where we can get the page directory of the kernel plus the virtual address space of the HAL heap, and we have an almost guaranteed address in virtual memory, which is either going to be FFD 000 or FFD 01000, which has a complete physical memory map. And remember the two problems we had with the USB 3380 was we needed to attack something below 4 gigabytes reliably, and we needed to know the physical memory map is, because if we touch an invalid page, we crash and the whole device goes offline. Now I know what's going to be an invalid page or not. So now I can attack the system. What do we do now? Well, we could attack the ACPI sleep interface. We could attack the ACPI tables, but those are all going to be complicated attacks, and they're going to rely on the machine going to sleep, or they're going to rely on the ACPI interpreter. We'd like to attack the OS itself. But the OS is likely going to be somewhere above the 4 GB range. So what we're going to do is we're going to attack EFI instead of attacking the OS. Now, EFI is something basically called runtime services. And what's interesting about EFI is that it still has to support 32-bit systems, especially because your CPU still boots up in 16-bit mode and then jumps in 32-bit protected mode, especially because you can still install 32-bit Windows on any laptop in the world. 32-bit Windows wouldn't know how to react to 64-bit physical addresses. And so EFI is guaranteed to have all of its allocations below the 4 GB range on any machine in the world. So if we can attack EFI, we don't need to worry about where the OS is. We can guarantee the presence of the pages below the 4 GB range. Now, attacking EFI sounds like something you can do at boot, but it's actually something you can do after boot as well, because EFI has a set of runtime services. And runtime services provide the operating systems with access to time, access to the ability to reset the system, access to environment variables, and access to updating firmware. And OS X, or Mac OS, and Linux and Windows, they all use EFI runtime services. So if we can patch those, we can then have our implant be called regardless of what the OS is. So we have to find where those runtime services are. They're described in a table called the runtime service table. This is allocated in the EFI pool, and the EFI pool has some nice little signatures that we can look for, one for free allocations, one for actual allocations, and one for the tail of the allocation. So in between a p0 and a ptal, there's going to be an allocation. And then the runtime services table itself has a signature, which is runtserv. So if I just scan all memory below 4 GB, and I jump over the addresses which I know are invalid because I've read the memory map in the ACPI BIOS multinode, I can find the runtime services table, and I can make sure I've got the right thing, because if I add up the header size, the tail size, and cross-correlated with the runtime table size, I can basically make sure I've got the right thing. And in a few slides, you'll see a picture of that. Now, the one difficulty is that Windows takes that runtime service table and virtualizes, aka maps in virtual memory, all of the functions and changes their address. Plus, if you have device guard turned on, it will in some cases run them in VTL1 as well. So Windows kind of changes all those pointers, moves them elsewhere, passes them to the HAL, and then the HAL hand selects only a few of those pointers and then stores them in another table. Which means that if you do find a table, the pointers in there are not going to be valid anymore because they're moved somewhere else. And number two, even if you find a table and patch it, Windows doesn't actually use a runtime services table. It uses its own copy of the table which is moved elsewhere. So this kind of sounded kind of depressing at first. However, for some interesting reason, when Windows patches the EFI, when it moves the EFI runtime functions elsewhere, it actually, I think accidentally or bizarrely, patches the runtime table with the address of the new functions. So even though nothing is going to use that runtime table anymore, Windows still takes care of updating the runtime table with where it put the functions, then makes its own table. So if we can actually still find the original firmware table, it'll have been patched by the OS with the new pointers. And on top of that, there are two pointers that it doesn't touch, which will have the physical address left in there. So graphically, I can explain this a little bit better. Here is essentially the EFI runtime table, and here is the pool header with a size of B0 and a type of 6, which means runtime memory. Then at the bottom, I've got the pool tail with the size of B0, and so in between, I've got the EFI runtime services. And there's a signature here that says runtserv. You can see all these pointers with FFFFFFFFFFF. This is where the kernel remapped the addresses. So I have their virtual address. And then in the middle, there's two functions that still have completely different pointers, which are the physical address. So they actually leak the physical address of at least two of the functions. Plus, if you do have virtual memory access to the page directory, you can get to the virtual functions as well. Now, what makes this even easier is that all the runtime functions in the firmware, they actually live in a PE file. So all those functions are actually going to be pointers to functions in the same PE file. So if you have the physical address of one of the functions, you can just look up until you find a PE header or MZ header, and then you know where the actual EFI runtime driver is. You can get its base address, and you can just do some simple math to figure out, well, okay, if this address physical is close to this address virtual, and I've got a PE header, I can figure out the diff, and I can get the physical address of all the pages. Or because we've got PML4, we could also just use the virtual addresses directly, right? Since we do have the kernel space directory, we can look up those addresses. But the point is we actually don't have to, because of the physical pointers leaking, we can get the virtual pointers as well. So now basically we can patch not the table, but one of the functions that's pointed to by the table with our own implant code. And the only thing that's left is getting the call, getting the implant to run. And this is unfortunately kind of an open problem, because Windows does not have a simple mechanism that's a non-admin you can use to basically get an EFI function to run. The BCD, which uses EFI, can only be accessed by admins. The firmware environment variables, even to read a firmware environment variable, you have to be an admin in Windows. So there's no command I've been able to find yet to force an EFI function to run, but periodically you're going to get things like the memory diagnostic, Windows Defender, volume snapshot, system restore. They will end up calling get variable at some point, and if you've hooked get variable, you will eventually get code execution. But you do have to kind of wait around for the system to be able to do that. So if someone figures out a way to trigger this, I'd welcome the input. So let me actually do a quick little demo. I'm going to plug in the PCI device here. I should probably turn off the power first. And then I'm going to use PCI Leech to try to get the runtime table, hoping that it works. Let's do it this way instead. Okay, so that's one end of that. Plug this in here. And hoping we'll get that little dig-a-doo sound. Okay, let's plug this here. So it has powered up. There's some LEDs. LEDs are good. And I'm going to allow the connection of the box. Okay, you didn't hear, but there was a little dig-a-dig-a-doo. And let me try to find my admin command prompt now. I should have it open. Oh, there it is. So I'm going to try one command, which is to search, actually to dump the, I reused the command called patch because I was lazy, but this should find the memory map. Boom. So it's called patch, has nothing to do with patch. What this command does is it looks up the ACPI bias multi-node, which again is going to be hard-coded in physical memory, or we can scan for it. And now I know exactly all the physical addresses on this laptop that I can access. Some of them are reserved, so I better not touch them. The ones that are not reserved, I can dump. Then I can search for the runtime table using that information. So I'll run a search. The search will take a little bit of time, and I don't know if you can see, but the LEDs are kind of blinking here to indicate that there's access going on, and this is going to be searching for the that runtime table. And if we find it, demo gods, it'll print out the function pointers and the data that's actually there. Again, this has to scan the entire address space, physical address space, because we don't know where the runtime table is going to be. We know it's below 4 gigs somewhere. Oh, and actually I should have passed in a flag to that, otherwise it's going to crash. So I'll do it one more time. While it's actually scanning, just to kind of conclude some thoughts here. So first of all, if you actually run Windows 10 with Hyper-V enabled, two things are going to happen. Is A, the firmware services are going to be in VTL1. They're going to be in the protected region of the hypervisor memory. And so if you do try to do a DMA attack against the EFI memory, you won't be able to. With device guard turned on, you're actually okay. But here's the interesting thing. They only run the firmware, this was on an earlier slide, they only run the firmware in VTL1 in the protected environment if it's actually not WXORX. So if your firmware developer, like on Surface, did the right thing and their firmware is not writable and executable, they actually don't protect it because they assume it's okay, it's not writable, everything's fine. They only protect it if it's actually writable and executable. They protect it in the hypervisor to make sure a ring 0 exploit can't attack it. So ironically, while trying to protect the firmware for ring 0 exploits, they deprotect it on most systems against DMA exploits. So if you have like vulnerable EFI firmware to ring 0 exploits, it'll be protected. If you have firmware that's not vulnerable because it's W, X, or X, they won't protect it with the IMMU, and then you can actually patch it with DMA. So that's kind of weird. The second thing is that memory that use less than 1 megabyte memory option. If you use BCD edit and set first megabyte policy to use all, this should make it a little bit harder for an attacker to find a low stub, because now you're going to be the corner case. You're going to be the corner case where allocations don't start at a megabyte, but they start at 4 kilobytes. So now that low stub is going to be somewhere in the middle of all the other allocations. Again, by default, the first megabyte policy is to ignore the first megabyte. That's why the only thing that ends up there is the low stub. And of course, if you have a laptop with Thunderbolt, don't use in Windows always enable, don't disable Thunderbolt security, and I would recommend not enabling things like always trust Dell Dock, and definitely don't enable Thunderbolt at boot, because that bypasses all of the security that Windows then gives you. There we go. So this finished, found EFI runtime services, and here's all the virtual addresses where the runtime functions are on the Dell. And again, notice these 2 pointers here, which are leaked physical addresses, which are not going to allow me to figure out where everything else is. You can't patch these 2 because nothing calls them. That's why they're still old. But you can now use this to patch everything else. So this now gives you a universal attack against Windows machines and even against Linux. Ulf actually redid a lot of this work earlier against Linux machines as well. So to wrap up, Joe and Ulf, obviously they're the ones who kind of figured out the USB 3380. They did the initial firmware for it. They did the original presentation on this, so they deserve huge kudos for helping me be able to do this version of the attack that focuses on Windows with Thunderbolt 3, and of course Snare and Trammel for all the Thunderbolt work they did before that. Also, a friend of mine from Microsoft, she allowed me to plug this device into her Microsoft corporate laptop for the first time to try out how things were working. And then at hex dump, I'm like, here's your corporate credentials. Here's your corporate password. Cool, it works. And I also really want to thank the recon organizers for doing an amazing job with the first recon Brussels. I think it's amazing. And I'm honored to have been here for the first one. So big shout out to everyone from recon who worked so hard to bring us here. So with that, I'll open it up to any questions, although I'm guessing some of you are getting hungry. But thank you again for your time, and thank you again for Recon for hosting me. It looks like we got one in the back.
So you made an assertion at the beginning that even if you run Thunderbolt in sort of the most secure mode where it's using a unique ID on the device and doing a challenge response, that it's actually only authorizing the bridge rather than the device. You're saying like you've got a dock, you're slapping in different PCI cards, and if you slap out a different PCI card, it'll still actually have authorized the dock, not the card. I don't think that's true. I think the thing is, I don't think there's any devices out that actually use the random ID, the unique ID in the challenge response protocol, so I don't think you could actually test it yet. But basically, it should be the actual PCI device itself, not like bridges in between, which are sending the challenges and doing the responses.
So you're saying the design is actually safe against this, but the implementation of the hardware is incorrect, right? I'm
saying that it's not the mode that like Dell uses by default. It was just one of those optional modes for the Thunderbolt security levels.
Sure, but what I'm saying is if I actually go in the BIOS and I enable that mode, which is an option, I've tried it out, and it still lets me. So if they haven't implemented,
that device is not actually a thing that. So you can turn on the mode, but basically, yeah. I mean, right. I guess that could be a Dell thing. Basically, they're turning on the mode and not actually enforcing the policy that they require the unique ID.
Which in my book is broken. It should have a warning saying, this is not supported or something like that.
Sure.
But thank you for clarifying that. Yep. Kind of like the old secure boot firmwares, which wouldn't actually check the signature of op ROMs. All right, anyone have any other questions? All right then. Bon appetit. Enjoy your lunch. Thank you very much.